Okay, and we're back, and we're doing a little bit more with projectiles. And in fact, we'll keep this kind of conceptual. I'm not going to worry about any math today, or at least for this video. This is more the properties of projectiles. Okay, just some kind of cool features of projectile motion, a little bit of trivia perhaps in certain cases. We're already pretty familiar with the fact that projectiles, okay, balls that you kick or throw, when they fly through the air, they go in that curved arch. Without air friction, that would be a parabola. Now, the reason for the parabola is the fact that you have two different motions. You've got forward motion, the horizontal motion, which is a constant velocity, and then you have gravity acting vertically, okay, always pulling down on it with a constant vertical acceleration. And it's that combination of constant speed sideways, constant acceleration downward that gives you the curve. And I have a separate video that gets into that a little bit more. Projectiles, when you have that parabola, they're symmetric in the sense of speeds. Okay, so if you were to slice a parabola in half, it's the same kind of curve on either side. And what this means is that at the same height, whether you're going up or coming down, at the same height above the ground, you have the same speed. And that's what I mean by like a symmetry when it comes to speed. Of course, when you get to the highest point, your vertical speed, at least, is going to be 0. That's when vertically the object stops. It has to stop in order to turn around and come back down, for example, if you threw it up in the air. What a lot of people forget about, though, is it's very tempting to say that even though it stops at the highest point, yeah, I guess for most people, the speed being 0 makes sense. What people often don't realize, though, is that the acceleration is not 0. Acceleration is caused by a net force. Gravity is the net force. Again, we're forgetting about air friction. We're ignoring it. So gravity is the only force that we consider acting on a ball that you tossed up in the air. And so it doesn't matter if it's moving or not. Gravity is still pulling on it. There still is a net force, meaning you still have the acceleration of gravity. That magic number of negative 9.8 meters per second squared, even though the ball has actually stopped. It only stopped for a split second. We call that the instantaneous speed is 0. But the acceleration, at every moment it's flying through the air, the acceleration is going to be 9.8 meters per second downward because of gravity. Now, there are some pictures that can help us with this. And I'm going to pull up some simulations. The first one here is the two balls are starting at the same height. We're just going to drop them straight down. Now, this would be true for any, hopefully you've done this before, where if you drop two different weights, they hit the ground at the same time. They accelerate at a constant 9.8 meters per second squared until they hit the ground. Again, assuming we can ignore air friction. What's cool about projectiles, though, is I'm going to give the lighter ball on the right, instead of just dropping it straight down with no sideways motion, I'm going to give it some horizontal speed. Okay, just a little bit there. And let me rerun it. Notice that even though it's moving forward a little bit, it still hits the ground at the same time. Okay, let me reset it. I'm going to make it go faster. It's kind of like if you're holding the ball and you just kind of push it or toss it sideways, or let it roll off a tabletop or something like that. If we give it some horizontal speed, I'll give it a little bit more now, and notice how, yeah, it's moving forward and the purple one is just falling straight down, but they land at the same time. And I'll max out the horizontal speed here. And the same deal. They hit the ground at exactly the same time. What this is showing, and what I'm trying to make a point of here, is that the two motions that we have going on simultaneously, the sideways or horizontal motion, the vertical falling due to gravity, they're independent of each other. They don't care about each other. What happens sideways, motion-wise, makes no difference as to what happens up and down. due to gravity. There is no sideways gravity, and so there's nothing to affect that sideways motion. So it really doesn't matter how fast you throw it forward. These two objects are going to be hitting the ground at the same time because the vertical motion doesn't care whether or not there is sideways motion. So that's an important point about how to do these multi-dimensional type things. Perpendicular motions are independent of each other. Another simulation, I'm just going to run this. It's again just kind of a ball. Imagine you're kicking a ball off the ground. What this one's showing though is the velocity vectors. Okay, it's another picture that you could have in your head. Notice that these arrows going sideways, the horizontal velocity, the Vx, it's the same length at every single position as it flies through the air. That tells us that the horizontal speed doesn't change. Okay, every second it moves the same distance forward. This is another way of thinking about that. Now vertically, check out what happens. When you throw or kick something up in the air, the upward speed is high. That's where it's moving the fastest, going up. It's the vertical velocity vector that gets shorter as you go up, because you're slowing down vertically as gravity is tugging on you. Here's that highest point. Here's the peak. Notice you still have a constant speed going sideways, but that's where your vertical velocity is actually 0. That's where up and down you stop, so you can turn around and start to fall back down. Now here you're at the same height. That's what I just mentioned. The vertical speeds are the same. The vertical velocities are not the same. They're in opposite directions, but the speeds, the length of that arrow there, is the same. At this height, okay, you're going a little faster up. You're going exactly the same speed coming down, opposite direction, and so on. We could do that for any height here. It's nice and symmetric, like a mirror image. If we cut the parabola in half, you'd have a mirror image on the two sides. Okay, so again, the vertical motion is different and independent of the horizontal motion. And last but not least, here's one where you kind of just toss something up, and it has a small forward speed. It's in the air for, I have a little clock over here, it takes 2 seconds. Okay, if it travels up 5 meters and then falls 5 meters, it takes 2 seconds. Now notice the time is the same going up as it is coming down. Again, symmetry that we have. That's 1 second to go up 5 meters, 1 second to fall down 5 meters. Okay. Let me go ahead and let it move a little faster forward. So in other words, the horizontal speed is going to be a little quicker. Nothing has happened to gravity though. So notice that it still takes only 1 second to go up and 1 second to come down. 2 seconds total in the air. Okay, but it moves farther forward because it's moving faster forward. The range is a little bit bigger, but that does not affect the vertical motion and the time that the object is actually in the air. And just for completeness, let me make it go as fast as we can in the simulation. You let it run. Doesn't make any difference. Yeah, it travels a lot farther horizontally because it's moving faster horizontally. But the time in the air, the acceleration, the gravity, the vertical motion, all of that is exactly the same as it was in the other cases. Okay? Independent motions. Okay, so all of these are just conceptually what happens with these projectiles. That independent motion is really the key to all this. Some other little tidbits. People find these to be kind of interesting. I'm not going to prove it. I'm not going to do the math. You can look that up in textbooks or online, or you might even do that in class or something. But what's cool about this, there's something special about complementary angles. In other words, angles that add up to 90 degrees. If you had a ball sitting there and you launched it at a certain speed, let's say 10 meters per second. If you launched it at 60 degrees, we know it's going to go up and it's going to land somewhere to the right. What's cool about this, though, is that if you were to launch the same thing still at 10 meters per second, but now instead of at 60 degrees, at 30 degrees, more shallow, it's still going to go flying forward and land in the same spot that it did at 60 degrees. Okay. And you could do it instead of 60-30, you could do it at 20 degrees and 70 degrees. As long as you launch it at the same speed, at complementary angles, you have the same range. Okay, they go the same distance and would land at the same spot. That's kind of a nice little bit of trivia. The maximum range, if you want to throw a ball the farthest, again, under ideal conditions, without air friction or anything weird going on, 45 degrees is the magic angle. Okay, that'll maximize how far it goes. Last thing I want to mention is and a really cool application of projectile motion is satellites, things in orbit around the Earth, or around any object, really. All satellites of any kind are projectiles. Something else got them going, and once you turn off the rocket or you let go of the thing when you're out in space, it's only under the influence of gravity. And that's our definition for a projectile. What's cool about satellites, though, is the fact that they're always in a state of free fall. Okay, so if you imagine a little satellite that you put up there, that NASA put up there or whatever, maybe a weather satellite or communication satellite, okay, in an orbit, what's cool about this is that its velocity is always tangent to the circle. Okay. Now, at the same time, the force that it feels, there's still gravity there. What do you think keeps it in orbit? The force of gravity is pulling straight down. So what's neat about this is in a circular orbit, the speed is constant, as if it's like if you just threw something forward, and it's falling, okay, because gravity's tugging on it, and that's what a projectile looks like. It's when you throw a ball, the same thing happens. But what's cool about this is that if you have a certain speed, called the orbital speed, if it's moving fast enough forward, as it falls, what's cool is that it matches the curvature of the Earth. Okay, and that distance between the satellite and the Earth stays constant, even though it's falling because of gravity. So that's a really cool application of projectile motion. It's also the reason, the fact that you're in free fall, things in free fall, if you placed it on a scale and you dropped the scale and the object at the same time, the scale would read 0 because they both fall at the same rate. There's no push between the object and the scale. And so you would look at the scale and see 0. You'd say that it's weightless. We call it apparent weightlessness. This is why you see astronauts floating when they're in orbit in the space station and things like that. Gravity is still really strong. Gravity is pulling them towards the Earth and making them fall. But since everything falls at the same rate, okay, that's what our little g in physics class stands for, the acceleration of gravity, everything has that same value. That's why you don't see them like standing on the floor. Everything floats because everything's falling. It's not true weightlessness. Okay? There's a lot of gravity there. That's one of the biggest misconceptions in science. It's because they're falling, because they're projectile. Okay, so hopefully this clears up some of the concepts behind projectiles, and now we can look at some other lessons where you throw in the math and you can actually predict and figure things out specifically. But it's all based on these same concepts. So until next time, we'll see you later.